Hello and welcome everyone. Myself Mijanur Rahaman and today my topic of discussion is erythropoiesis. Today we will discuss about the definition, the site of erythropoiesis in fetal life, in newborn babies, in children and in adults. Process of the erythropoiesis and factors that are necessary for erythropoiesis. So take a look. First of all, what is erythropoiesis? Erythropoiesis is a process of the origin, development, and maturation of erythrocyte. So, what is erythropoiesis? Erythropoiesis is a process through which the origin, the development, and the maturation of erythrocyte or RBC occurs. Now, one term also available, that is hemopoiesis or hematopoiesis. What is this term? This is the process of origin, development, and maturation of all the blood cells. So don't confuse between hemopoiesis or hematopoiesis and erythropoiesis. Erythropoiesis is specifically the process of origin, development, and maturation of erythrocyte, and hemopoiesis is in general. It is the process of origin, development, and maturation of all blood cells. So I think you have cleared this concept. Now, site of erythropoiesis. First of all, in the fetal life, the erythropoiesis generally occur in three stages. During the first 2 months or first 2 months of their intrauterine life, the RBC are generally produced from the mesenchyme of yolk sac, and this stage is known as mesoblastic stage. Then, hepatic stage. From the third month of the intrauterine life, liver is the main organ that produces RBCs, and spleen and lymphoid organs are also involved in erythropoiesis. And the last stage, during last 3 months of the intrauterine life, the RBC are produced from red bone marrow and liver. This is myeloid stage. In the first trimester, mesenchyme of yolk sac, mesoblastic stage. Second trimester, hepatic stage from liver, spleen, and lymphoid organ. And in the third trimester, it is myeloid stage from bone marrow and liver. Now, in newborn babies, children, and adults. In newborn babies, growing children, and adults, RBCs are produced only from the red bone marrow. There are two stages. Up to the age of 20 years, RBCs are produced from red bone marrow of all bones. All bones means all bones like long bones and all the flat bones. But after the age of 20 years, RBCs are generally produced from the membranous bones like vertebra, sternum, ribs, scapula, iliac bones, skull bones, and from the ends of the long bones. Because, what is the reason behind this? Because after 20 years of the age, the shaft of the long bone becomes yellow bone marrow because there is occurrence of fat deposition, and when the yellow bone marrow occurs, this loses the erythropoietic function. In adults, liver and spleen may produce the blood cells if the bone marrow is destroyed or fibrosed. Collectively, bone marrow is almost the equal to the liver in size and weight. It is also active as liver. Though bone marrow is the main site to production of all blood cell comparatively, 75% of the bone marrow is involved in the production of leukocyte and only 25% is involved in the production of erythrocyte. But still the leukocytes are less in number than the erythrocyte. The ratio is 1:500. This is mainly because of the lifespan of these cells. Lifespan of erythrocyte is 120 days, whereas the lifespan of leukocyte is very short, ranging from 1 to 10 days. So the leukocytes need larger production than erythrocytes to maintain the required number. Now we will go and discuss the process of erythropoiesis. First of all, we have to know what is stem cell. Stem cells are just those cells which are primarily capable of self-renewal and differentiating into specialized cells. So stem cells are the sum of the group of cells which have the capability to self-renewing and differentiating into specialized cell. And hematopoietic stem cells are the primitive cells in the bone marrow which give rise to the blood cells. So what are the stem cells present in the bone marrow which acts as a stem cell in bone marrow for the formation of blood cells? It is hematopoietic stem cells. And hematopoietic stem cell in the bone marrow are also called uncommitted pluripotent homeopoietic stem cell. What is the term? Uncommitted pluripotent hemopoietic stem cell. So these uncommitted pluripotent hemopoietic stem cells are defined as the cell that can give rise to all type of blood cell. In early stages, we can shortly called PHSC are not designed to form particular type of blood cell, and it is not possible to determine the blood cell to be developed from these cells. Hence, the name uncommitted PHSC is given. In adults, only a few number of these cells are present, but the best source of these cells is umbilical cord blood. When these cells are designed to form a particular group of blood cell, these uncommitted PHSC are also then called committed PHSC or committed pluripotent hemopoietic stem cell. So there is conversion of uncommitted pluripotent hemopoietic stem cell to committed pluripotent hemopoietic stem cell. Now, this committed pluripotent hemopoietic stem cell will give a specific type of blood cell. Now, committed pluripotent hemopoietic stem cells are also two types. One is lymphoid stem cell, which give rise to the lymphocyte and natural killer cells, and another one, the colony forming blastocytes, which give rise to the myeloid cell. And myeloid cells are the blood cells other than lymphocytes. When grown in culture, these cells can form colonies, hence the name colony forming blastocytes. Different units of colony forming cells are: one is colony forming unit erythrocyte, which will form the erythrocyte. So colony forming unit erythrocyte are those group of cells of this unit which helps in the development of erythrocytes. Now second one, colony forming unit granulocytes or monocytes, CFUGM. These cells give rise to the granulocytes, neutrophil, basophil and eosinophil and monocyte. So these cells can give rise to granulocytes like neutrophil, basophil, eosinophil and monocyte. Colony forming unit megakaryocytes, so CFUM. This group of cell will give rise to platelet are developed from these cells. So one is CFUE, colony forming unit erythrocyte. Second one, colony forming unit granulocyte or monocyte. Then number 3, colony forming unit megakaryocyte, CFUE, CFUGM, CFUM. Now we will discuss about the changes which occur during the process of erythropoiesis. When the cells of CFUE or colony forming unit erythropoiesis erythrocytes are passes through the different stages and finally become the matured RBC. During these stages, 4 important changes are noticed. Number 1, reduction in the size of the cell from the diameter of almost 25 to 7.2 micron and disappearance of nucleoli and nucleus. Then appearance of hemoglobin and change in the staining properties of the cytoplasm. So what are the changes? One is reduction in size of the cell, one is disappearance of nucleus and nucleoli, one is appearance of hemoglobin, and another one is change in staining properties of the cytoplasm. Now let a look. Uncommitted pluripotent hemopoietic stem cell to committed pluripotent hemopoietic stem cell. Now committed pluripotent hemopoietic stem cell are two types. One is lymphoid stem cell and another one is colony forming blastocyte. Lymphoid stem cell give rise lymphocyte. Now colony forming blastocyte will give rise to colony forming unit erythrocyte, colony forming unit GM, colony forming unit M or megakaryocyte. Now CFUE RBC and colony forming unit GM to granulocyte and monocyte. In the granulocyte, neutrophil, basophil, eosinophil, and megakaryocyte from CFUM, and also platelet are from this layer. Now we will discuss about the stages of erythropoiesis. Various stages between CFU cells and mature RBC are: first of all, pro-erythrocyte or pro-erythroblast, then early normoblast, then intermediate normoblast, then late normoblast, then reticulocyte, and the last stage is matured erythrocyte. So first, let's discuss. First of all, we look at the diagram. This is the diagram. Pluripotent hematopoietic stem cell, two colony forming blastocyte, two colony forming unit erythrocyte, two pro-erythrocyte, two early normoblast, then intermediate normoblast, then late normoblast, then reticulocyte and erythrocyte, and the another one are for another group of blood cell. Now discuss about each step with little bit of discussion. First of all, pro-erythroblast or megaloblast. Pro-erythroblast or megaloblast is the first cell derived from the CFUE. It is very large in size with a diameter of about 20 micron. Its nucleus is large and occupied the cell almost completely. The nucleus has two or more nucleoli and a reticular network. Proerythroblast does not contain any hemoglobin. The cytoplasm is basophilic in nature, and proerythroblast multiplies several times and finally forms the cell of the next stage called early normoblast. Though the hemoglobin does not appear in this stage, but the synthesis of hemoglobin starts in this stage. So it is an important phenomenon. You must remember it. However, appearance of hemoglobin occurs only in the intermediate normoblast. Now, early normoblast. The early normoblast is little smaller than the proerythroblast with a diameter of about 15 micron. In the nucleus, the nucleoli disappear. The condensation of chromatin network occurs. The condensed network becomes dense and the cytoplasm is basophilic in nature. So this cell is also called basophilic erythroblast. The cell develops into a next stage called intermediate normoblast. So in this stage, the important phenomena is disappearance of nucleoli. Next stage, intermediate normoblast. Cell is smaller than the early normoblast with a diameter of about 10 to 12 micron. The nucleus still present, but the chromatin network shows further condensation. The hemoglobin starts appearing. Cytoplasm is already basophilic. Now, because of the presence of hemoglobin, it stains with both acidic as well as basic stains. So, these cells is called polychromophilic or polychromatic erythroblast. The cell develops into next stage called late normoblast. The important phenomena in this stage is appearance of hemoglobin. Now, late normoblast. Diameter of the cell decreased further to about 8 to 10 micron. Nucleus become very small with very much condensed chromatin network and it is known as ink spot nucleus. So in which stage you can see ink spot nucleus, it is late normoblast. Quantity of hemoglobin increases and the cytoplasm become almost acidophilic, so the cells is now called orthochromic erythroblast. In the final stage of the late normoblast, just before it passes to the next stage, the nucleus disintegrates and disappears. The process by which the nucleus disappears is called pyknosis. The final remnant is extruded from the cell. Late normoblast develop in the next stage called reticulocyte. Reticulocyte is otherwise known as immature RBC. It is slightly larger than matured RBC. The cytoplasm contains the reticular network or reticulum, which is formed by the remnants of disintegrated organelles. Due to the reticular network, the cell is called reticulocyte. The reticulum of reticulocyte stains with supravital stain. In newborn babies, the reticulocyte count is 2% to 6% of RBC, and 2 to 6 reticulocytes are present for every 100 RBCs. The number of reticulocytes decreases during the first week after birth. Later, the reticulocyte count remains constant at or below 1% of RBC. The number increases when the production and release of RBC increases. Reticulocyte is basophilic due to the presence of remnants of disintegrated Golgi apparatus, mitochondria, and other organelles of cytoplasm. During this stage, the cells enter into the blood capillaries through capillary membrane from site of production by diapedesis. So, what is the name of the process? Diapedesis. Important event during erythropoiesis given in table 10.1 and matured erythrocyte. Matured erythrocytes are those in which reticular network disappears and the cell becomes mature RBC and attains the biconcave shape with the help of spectrin, actin, ankyrin, band 4.1. These proteins helps the cell decreases in size to 7.2 diameter, 7 to 7.2 micron diameter. The matured RBC is with hemoglobin but without nucleus. It requires 7 days to develop a maturation of RBC from proerythroblast. It requires 5 days to up to the stage of reticulocyte, and reticulocyte take 2 more days to become mature RBC. So important events, let us look. Proerythroblast, important event, synthesis of hemoglobin starts. Early neuroblast, nucleoli disappear. Intermediate neuroblast, hemoglobin starts appearing. Late neuroblast, nucleus disappears. Reticulocyte, reticulum formed. Matured RBC, reticulum disappears. Cells attains biconcavity. Now, one important topic also, factors which are necessary for erythropoiesis. Now, development and maturation of erythrocyte varies. Development and maturation of erythrocyte require variety of factors which are classified into 3 categories. One is genital factor, one is maturation factor, one is factors necessary for hemoglobin formation. First of all, general factors. General factors necessary for erythropoiesis are erythropoietin, thyroxine, hemopoietic growth factor, vitamin, this type of general factor. First of all, erythropoietin. Erythropoietin is the most important general factor for erythropoiesis. It is the hormone called erythropoietin. It is also called hemopoietin or erythrocyte stimulating factor. It is a glycoprotein in nature and with 165 amino acid. This is secreted by kidney, specifically the peritubular capillaries of the kidney. A small quantity is also secreted from liver and brain. Stimulant for secretion. Hypoxia is the stimulant for the secretion of erythropoietin. Now, actions of erythropoietin. Erythropoietin causes formation and release of the new RBC into circulation. After secretion, it takes 4 to 5 days to show the action. Erythropoietin promotes the following processes: production of pro-erythroblast from CFUE of the bone marrow, then development of pro-erythroblast into matured RBCs through the several stages: early neuroblast, intermediate neuroblast, late neuroblast, and reticulocyte. Then release of matured erythrocytes into the blood. Even some reticulocyte like immature erythrocyte are released along with the matured RBC. Blood levels of erythropoietin increase in anemia. Next, thyroxine. Being a general metabolic hormone, thyroxine accelerates the process of erythropoiesis at many levels. So hyperthyroidism and polycythemia are common. Next, hemopoietic growth factors. Hemopoietic growth factors of growth inducers are the interleukins and stem cell factor. Generally, these factors induce the proliferation of PHSCs, and interleukin are glycoprotein which belong to the cytokine family. So, interleukin involved in erythropoiesis. Interleukin 3 secreted by T cells, interleukin 6 secreted by T cells, endothelial cells, and macrophages. Interleukin 11 secreted by osteoblasts. Next, vitamins. Some vitamins are necessary for the process of erythropoiesis. Deficiency of these vitamins cause anemia because these are anemia. These vitamins causes anemia associated with the disorder. First of all, vitamin B. Vitamin B deficiency causes anemia and pellagra, diseases characterized by skin lesions, diarrhea, weakness, nervousness, and dementia. Vitamin C, its deficiency causes anemia and scurvy, ancient disease characterized by impaired collagen synthesis, resulting in rough skin, bleeding gum, loosening of teeth, poor wound healing, bone pain, lethargy, and emotional damages changes. Vitamin D, its deficiency causes anemia and ricket. Vitamin E, its deficiency leads to anemia and malnutrition. Now, maturation factors. Maturation factors are vitamin B12, intrinsic factor, folic acid are necessary for the maturation of RBC. First of all, vitamin B12, cyanocobalamin. Vitamin B12 is the maturation factor necessary for erythropoiesis. Vitamin B12 is called extrinsic factor since it is obtained mostly from diet. Its absorption from intestine requires the presence of intrinsic factor of Castle. If the intrinsic factor of Castle is not present, then vitamin B12 cannot be absorbed. So, vitamin B12 is stored mostly in liver and in small quantity in muscle. When necessary, it is transported to the bone marrow to promote the maturation of RBC. It is also produced in the large intestine by intestinal flora. Action. Vitamin B12 is essential for synthesis of DNA in RBC. Its deficiency leads to failure of maturation of the cell and reduction of the cell division. Also, the cells are larger and fragile and weak. The cell membrane resulting in macrocytic anemia. Vitamin B12 deficiency causes pernicious anemia, so vitamin B12 is anti-pernicious factor. So, which vitamin is known as anti-pernicious factor? It is vitamin B12. And which vitamin deficiency can cause pernicious anemia? That is vitamin B12. Now, intrinsic factor of Castle. Intrinsic factor of Castle is produced in gastric mucosa of the parietal cells of the gastric glands. It is essential for the absorption of vitamin B12 from intestine. In the absence of intrinsic factor, vitamin B12 is not absorbed from the intestine. This leads to pernicious anemia. Deficiency of intrinsic factors occurs in severe gastritis, ulcer, gastrectomy. Now, there is one principle known as hematinic principle. Hematinic principle is the principle thought to be produced by the action of intrinsic factor on extrinsic factor. It is also called anti-anemia principle. It is a maturation factor. Now, folic acid. Folic acid is also essential for maturation. It is required for the synthesis of DNA. In the absence of folic acid, the synthesis of DNA decreases, which causing failure of maturation. This leads to anemia in which the cells are larger and appear megaloblastic or pro-erythroblastic stage, and anemia due to folic acid deficiency is called megaloblastic anemia. Factors necessary for hemoglobin formation. Various materials are essential for the formation of hemoglobin in the RBCs. Deficiency of these substances decreases the production of hemoglobin, leading to anemia. Such factors are first-class proteins and amino acids. Proteins of high biological value are essential for the formation of hemoglobin. Amino acids derived from these proteins are required for the synthesis of protein, part of hemoglobin, i.e., the globin. Iron, necessary for the formation of heme part of the hemoglobin. Copper, necessary for the absorption of iron from GI tract. Cobalt and nickel, these metals are essential for the utilization of iron during hemoglobin formation. And vitamins, vitamin C, riboflavin, nicotinic acid, and pyridoxine are also essential for the formation of hemoglobin. So this is for now. Today we have also completed a major topic and most important topic of also the erythropoiesis. So I think I have cleared all the concept very carefully. If you have any query or any doubt, please comment down in the comment section. I will try to give reply to those questions and doubts, and also suggest me in which topic you want the next video, and thank you for watching.